Yeah, good evening, everyone. So let's start with today's session. Now you can stop chatting in the chat box. So this is third session and we'll be discussing prime numbers and many of interesting properties of prime numbers via problems. Yeah. So last time we did divisibility and this is something in connection with that. So again, this topic is a topic from number theory. And it's very important as far as number theory is concerned for various reasons. One reason is every integer we can generate through product of primes, or every number I can factorize as product of primes. So they are called as building blocks of integers, and that's why they are important. So if you understand their properties, then that helps in understanding the properties of integers. Secondly, nowadays, maybe after 1960, primes were used for security systems or crypto systems like RSA, EFS, etc. And that's one reason why primes are practically important nowadays. Yeah. So let's recall the definition of divisibility. So we said 3 divides 12, and this was the notation. Why? Since 12 I can write as 3 into something, 3 into some integer, that is 3 into 4. So we say 3 and 4 are factors or divisors of 12. Okay. Now for 12, can you tell me all positive divisors?
Sir, in the chat box.
12.
Sir, in the chat box to everyone.
Now you can just say orally.
Sir, 1.
Yeah, 1.
2, 3.
Just a minute. Just a minute. So I want to write with pairs 1 and 12.
Sir, 1 and 12. 2 and 6.
That's 1 into 12, right? And then
1, 12. 1 and 12. 2 and 6. 2 and 6. 3 and 4. 3 and 4. 3 and 4. That's it. That's it.
Yeah. Okay.
1, 2, 3, 4, 6, 12.
Yeah. So now let me say more generally, for every number n, two sure divisors are 1 and number itself are always divisors. And that you can see even with the example of 12, you said 1 and 12 are divisors. Okay. Now there are some numbers for whom only divisors are 1 and n.
Sir, prime numbers.
And such numbers we call as prime numbers. And numbers like 2, 3, 4, 6 in case of 12 are called as proper divisors. So those numbers which are proper divisors, they are called as composite numbers. So I'll go to next page and define properly what is prime, what is composite, and then we'll go ahead. Somebody's audio is on, some disturbance is there. Yeah, so far good. Shall I go to next page?
Yes. Yes, sir.
Yeah. Okay, so I want to define precisely what is prime number. Definition.
Sir, can I tell?
Wait, I'll write. Just a minute. So I want to say some points. A natural number n greater than 1. So by very definition, 1 is not prime. We define prime as number greater than 1. Okay. And these definitions are made by great mathematicians so that the theory works smoothly further. So there is no challenge why we should take this as definition. But of course, there are some conveniences why we take n greater than 1. So a natural number n greater than 1 is called as a prime. Is called as a prime or a prime number if its only positive divisors are
One and the number itself.
1 and n itself.
It doesn't have any more factors or divisors.
Yeah, so which means they have exactly 2 divisors. So that is, in other words, they have exactly 2 divisors, right? Exactly 2 divisors. Okay, and so maybe I'll say as a remark, but its definition, a natural number n greater than 1, which is not a prime, is called as composite. Which is not a prime is called as a composite number.
Yes, sir.
So a composite number is a number which has more than 2 factors.
Yes, has proper divisors other than 1 and the number
Yes,
itself. Okay, so that is, they have proper divisors or more than 2 divisors.
2 or more divisors.
But 2 divisors will give you a prime
No,
number.
not two divisors. Yeah. So exactly 2 divisors is a case of prime. Those which have more than 2 divisors are composite. Yeah. So let's go to the first question and step by step we'll look at properties of primes. Question is very simple and don't disclose the answers. You can write answer in chat box, but first listen to the question. Okay, so question is write primes between 1 to 100. And what I want is you write in your notebook prime numbers between 1 to 100, but in chat box, you just tell me the number of primes between 1 to 100. Okay, and perhaps some of you may be knowing the answer, that how many primes are there between 1 to 100, but don't simply write in chat box. We want numbers between 1 to 100, primes between 1 to 100, okay, for some further problems. So it's better you list all primes between 1 to 100 in your notebook, and in chat box write only to me, don't disclose the answer, the number of primes between 1 to 100. Okay, is the question clear?
Yes, sir.
Yeah. Yeah, Shreyas, I guess perhaps you might be knowing the answer, but write down all primes in your notebook, right? Because we need them later. Shrestha, good. Yeah. So by our very definition, note 1 is neither prime nor composite for certain reasons.
Sir, can you repeat?
Yeah, according to our definition, number 1 is not prime as well as it is not composite.
Yes, sir.
Sir, even 0 is like that, right?
Yeah, so we are here we are talking of natural numbers. So that is 1 and greater than 1. So
Okay.
we don't talk of 0. But anyways, if you want to think about 0, note that 0 has many divisors. In fact, infinitely many divisors. Every number divides 0. Fine. So
Okay, sir.
and classically, in fact, all these definitions results were developed by Euclid and in his book Elements. And in those days, they were dealing only with natural numbers. They were not comfortable with negative numbers, or in fact, 0 was not accepted as a symbol, as a number in those cultures. And because of absence of 0, there were no negative numbers. So in India,
I read in a book that 0 was invented in India.
yeah, so 0 was in fact, in various cultures there was already 0, but not as a symbol, not as a number. And Indians were the first one who introduced 0 as a number, as a placeholder, as a symbol. And Brahmagupta gave rules of addition with 0, multiplication with 0, etc. And with that, he also introduced negative numbers. But in many countries or many cultures, even people were not comfortable with negative numbers. So, for example, Bhaskaracharya's Leelavati, so that is a book from 12th century. And at some points, at some places, he mentions that one answer is negative, but people are not comfortable with negative numbers, so we won't accept
Can you hear me?
negative answers.
Sir, wasn't it Aryabhatta?
Aryabhatta wrote Aryabhatta. Leelavati was by Bhaskaracharya II.
No, something 0 is I think by Aryabhatta, right?
Not exactly by Aryabhatta, but Aryabhatta gave rules of addition, multiplication by 0. So somebody must have used that 0 as a symbol, as a number during that period. But not exactly Aryabhatta. There is no proof that Aryabhatta invented 0.
Sir,
Yes?
sir, I sent my answer.
Just a minute. Who is that, Pranav?
Yes, sir.
Yes, that is correct.
Sir, I sent 2 answers, sir. The second one is correct.
Sir, I sent an
Yeah.
answer.
Sir, I sent an answer. Could you check? I'm Bhargav.
Yeah, Bhargav, this is something wrong. I mean, you have overcounted. They are not those many. Little lesser than that.
Sir, I sent you my answer. I am Kavisha.
Kavisha, yeah, that is correct. Your answer is
Sir,
correct.
I'm Anumega. I have also sent my answer. Is it correct?
Anumega, I don't want the list of all numbers. That I'll do here, but I want how many numbers are there. You just count how many primes you are listed, and just
Okay, sir.
Sir, my name is Aditya. I have also.
yeah, that is your answer. Yes, Sanjana Sri.
Yes.
Answer is correct. Then Nove. Yeah, Atul.
Sir, I sent.
Sir, it is correct.
Atul answer is correct. And who is this? Anumega. Yes, Anumega answer is correct.
Sir, is my answer correct?
No way. I think you have missed one number.
Then 25 primes.
Yeah, don't disclose the answer.
Okay, sir.
Okay, so I think enough time is given now, and we'll start with listing all those prime numbers. So So let me go to the next page.
Sir, I'm Nikhil Madhavesan, the answer.
Yes, Samrata. Now let me start with the actual listing of numbers. Nikhil, yes, correct. Yeah. Okay, so numbers, prime numbers between 1 to 10. We'll
Sir, can I go?
note in groups of 10. So what are the prime numbers between 1 to 10?
2, 3, 5, 7.
2, 3, 5, 7. 2, 3, 5, 7. 2, 3, 5, 7.
5, 7. So there are 4 numbers between 1 to 10. And check if there is some good pattern between the number of primes in every 10 numbers. So 11 to 20, what are the prime numbers?
11, 13,
11, 13, 17, 19.
11, 13, 17, 19.
Yeah. So there are once again 4 prime numbers. 21 to 30,
23 and 29.
23 and 20.
23 and 29. So you see now there are only 2 prime numbers. So the prime numbers are not uniformly spread. That's one thing is clear from this pattern. Then 31 to 40,
31 and
31,
37.
37.
31, 37.
31, 37. What about 39?
39 is divisible by 13. 13 threes are 39.
Very good. Yeah. So there are only 2 primes. Then 41 to 50,
41,
41,
47.
44.
41 and
41, 43 and 47.
47.
41,
Very good.
43, 47.
Yeah, very good. So now you see again the number of primes is increased by 1. There are 3 primes. Earlier 2 groups of 10, there were 2 primes, but now there are 3. 51 to 60.
53 and 59. 53 and 59.
What about 57?
No, sir, it is divisible. 57
is divisible by 13 and 3. Yes.
Divisible by 3.
So
Yeah.
19 and 3. So 19 and 3.
19 threes are right. 19.
Yes, sir.
Then so far good. 61 to 70.
61
67.
61 and 67.
And you see again there are only 2 in this group of 10 integers. 71 to 80.
71,
71, 73, 79.
71, 73 and 79.
What about 77?
77 and 11, 7.
77.
So
Yeah.
11 sevens are 77.
Yes.
It's divisible by 7.
Yeah. So there are now 3 numbers here, right? So again, the number of primes is increased by 1, and which means there is no good uniform pattern as far as distribution of primes is concerned, right?
Yes, sir.
So then 81 to 90.
81, 83, 89. 81, 83. No, 9 names are 81.
81 is divisible by 9.
Yes, 9 names are 81.
83 and 89.
83.
83 and 89.
Yeah. So again, there are only 2. And
90 to 100, there is
But there's only one side.
97. 97. 97.
97. So only 97.
yeah. Now add up all these. Yes.
So 91 is divisible by 7.
91. Yeah. 91 is 13 sevens. So it's not prime.
So 99.
99 is
99 is 11, 9s are 99.
99 is also divisible by 3. It is divisible by 11.
yes.
Divisible by 9.
Yeah.
Okay, so now add all these numbers and check what is this number. So that's the answer for my question. How many prime numbers are there between 1 to 100?
25. sir.
25.
So
25.
this sum is 25, right?
Yeah.
Six.
Just check your answers whether you have got 25 primes between 1 to 100.
Yes, sir.
Yes, sir.
Sir, I got 24.
Yes, sir.
So Nove, you just note which you miss out of this.
Sir, I missed the time number. Sir, I missed this 83.
83. Okay. Okay.
There is a
Yes.
91 a prime number.
Which one?
91.
91 is 13 into
13
7.
times 7.
So it has proper divisors. Okay, now let me define some function. So we define function pi of x. Pi of x. Pi stands for p stands for primes, and we define pi of x equal to number of primes less than or equal to x. Okay, so for example, we just calculated that pi of 100 is 25. Number of primes less than or equal to 100 is 25.
Okay, sir.
And let me tell you, there is no nice formula for pi of x, but there is one great theorem, very important result in number theory. You may not understand everything right now, but let me just give the statement. That's known as prime number theorem. It's due to Gauss. Prime number theorem. And we say the number of primes up to x is approximately equal to or is of order x by log x. Now perhaps you may not be knowing what is log x. So maybe after some years you'll understand what is this function log x, and this number estimates the number of primes up to x. So pi of x is almost equal to x by log x, almost equal to. I'm not saying exactly equal to. And what this sign means is, as x increases, error is reduced, and pi x is almost equal to x by log x. That's what it means.
Sir, but how is pi into 100 is equal to 25?
500 is number of primes.
3.14 into 100 is 314, right?
No, this is not pi into x. This is not pi into 100. We are defined this function. Pi of x is equal to what? Number of primes less than or equal to x. So for example, pi of 100 is number of primes less than or equal to 100, which we have just calculated that this number is 25. It's not pi into 100. It's
Sir, I didn't understand why the term pi is used here.
why that term pi is.
Because pi into x is not 25.
It's not pi into x. It is pi of x. That is symbol for function. It's a function. See, like for example, if I say s of x is equal to x square, this is called a square function. So s of 2 will be 4, s of 3 will be 9. Such a thing is called as function.
Excuse me, sir.
Yes.
Sir, you have written here that x upon log x is 25 if we take it into consideration. But if we take it for 100 into consideration, the answer will be 50.
Answer is not exactly equal to. So that's why I'm not saying pi x is equal to x by log x. I'm saying pi x is almost equal to x by log x. That's what it means. And this log is not to base 10. This log is to base e. This is something from calculus.
But why is pi used to represent prime as a function?
It's a notation for functions. Functions are denoted by various notations like f of x, l of
Sure.
x, e of x, and so on.
If pi is used as a variable over here, we can write give any sign or any number.
Krishna, pi is not used as variable. X is variable, but pi is later used for function.
The pi's value is 3.14, right?
No, this is not that pi. This is just some function, notation for function, and functions are represented like f of x, g of x, h of x. In this case, it is denoted by pi of x. That pi stands for p, and p stands for prime. So maybe after after few years, you'll surely understand all these notations. Perhaps right now.
So, then pi is considered as it is prime.
But see, for example, let me tell you the notation. If I say pi of 10, it means I'll explain with example. If I say pi of 10, it means number of primes up to 10. And how many primes are there up to 10?
4.
4. So I'll say pi of 10 is 4. Okay.
Then in this the pi is equal to prime.
Yeah. Very good. Yeah.
Okay.
So pi of 20 is 8. Pi of 30 is 4 plus 4 plus 2. Pi of 30
10.
is 10. And on same lines, if I work primes up to 100, pi of 100 is 25.
25.
Is that clear, everyone?
Yes, sir.
Shall we go ahead?
Yes, sir.
Yes, sir.
Yes, sir.
So before
Yes, sir.
we go ahead, I want to make one remark about this set of primes between 1 to 100. I see that there is only one even number, namely 2. Rest all are odd. Right? So I'll write remark.
Sir, because 2 is not there's no factor for 2 other than 1 and 2 itself.
2 is the only even prime number.
Yeah. So 2 is the only even prime. Because note once 2 is prime, every multiple of 2, 4, 6, 8, etc. have a proper factor 2. And therefore, other even numbers can't be prime. Is this fact clear?
Yes, sir.
Yes, sir.
Sir, I have a doubt. Can there be negative prime numbers?
Yeah, that's a very good question. Yeah, I'll try to answer your question. Just a minute. I'll go to next page. In fact, once again, classically, these concepts were developed by Euclid, etc. And in that period, they were dealing only with positive numbers, natural numbers. So Euclid's period is little after Pythagoras. So they were dealing only with positive natural numbers. And therefore, all these concepts traditionally are defined for positive numbers. But in modern mathematics or in higher mathematics, something like integers, we have a concept of what is called as integral domain. Integral domain. It's generalization of set of integers, and there we define primes in a little different fashion. We don't define primes in this fashion. We define prime as number p is prime if p divides ab implies either p divides a or p divides b. That is the definition of prime in higher domains. In set,
Sir, can you please repeat?
Yes. So there are some sets which are generalizations of integers, and they are called as integral domains. And in these sets, there is a little different definition of primes, which says p divides ab implies p divides a or p divides b. That is a prime. And with this as my definition, even I can think of -2, -3, -5 as primes with this as a definition. But classically, or traditionally, we don't take negative numbers as prime numbers because they were developed in the period where people were dealing only with positive natural numbers. Yeah. Is that clear?
Yes, sir.
Are you convinced? Yeah.
Yes, sir.
Yes.
Okay. By the way, let me just comment on this definition. even in case of integers, this definition holds true. Like for example, if 4 divides product of two numbers, say for example, 4 divides 2 into 6. Shall I say 4 divides 2 or 4 divides 6? One of them. Is it true?
Nothing,
No.
nothing is true.
Yeah, that is not true. So more generally, for a composite number, if composite number, or say for example, 4 divides AB does not imply 4 divides A or 4 divides B. That is not true. But for primes, this is true, and it can be proved as a property that is called as Euclid's lemma. So even in integers, this property holds for prime numbers, not for composite numbers.
I did not understand the definition exactly what you mean when you say P divides AB is same as P divides A or P divides B.
So that is typically property of prime numbers. So for example, if 3 divides product of two numbers, say product of two numbers, then 3 divides one of them completely. So implies 3 divides A or 3 divides B, one of them. And this is taken as a definition in higher domains, in sets which are generalizations of integers. And with this as my definition, I can think of -2, -3, -5 also as primes.
So, but if I say 6 divides 2, 6 divides 2 and 3, then 6 will also divide 2 and 6 will also divide 3.
No, that is not true. 6 divides 2 into 3, but 6 does not divide 2, nor 6 divides 3. So what it means, so 6 is not prime. 6 is not prime. Okay?
Okay, sir. Yes, sir. So, means if we take 4 and we take the two A and B, the two numbers as 2 and 8, and we divide 4 by 8. Only one number is getting divided. So why it is not a prime?
No. So question is it true for every such pair? So for example, let me give you, so because you are giving 2 and 8, 4 divides one of them. But in general, if 4 divides product of two numbers, can you surely safely say that 4 either divides A or 4 divides B, one of them, always? Not just for one example. Is it true always? So for example, 4 divides 2 into 10. Is that right?
Yes.
Yeah. But can you say 4 divides 2 or 4 divides 10?
No, sir.
That is not true. Okay. So this property is not always true for 4. So which means 4 is not prime.
Sir?
Yes.
Sir, what if the case is where P is 2 and A is 5 and B is 7?
What?
Sir, where P is 2, A is 5 and B is 7.
P is 2, A is 5, and B is 7. But 2 does not divide 5 into 7. That is not true.
So what is the usage of prime in our life? Because we've been learning it, but how is it used?
See, one main point about primes is every number, every integer, you can factorize as product of primes in a unique way. That is called as unique factorization theorem. So, for example, if I give you, if I give you, say, for example, 72. 72 I can write as 2 into 36, and 36 is not prime. I can further factorize it. So it's 2 into 18.
Yes, sir.
18 I can write as 2 into 9. 9 is not prime. I can write this as 2 into 2 into 2 into 3 into 3. And this is called as prime factorization. So every number I can break into the product of primes.
No, until it becomes the prime number.
So that is one reason primes are important. And if you can understand the structure of primes, then structure of integers will be more clear, or we can understand more properties about integers. That is,
Sir, one doubt, sir.
uh,
Sir, you said you want to use for prime number, no, sir?
hmm,
Why you use 36 and 18?
36 is 2 into 18. Is that right?
Yes, sir.
Yeah. So I want to factorize. I want to factorize number till I get prime factors. So shortly, this I write as 2 into 2 into 2 3 times. So 2 cube into 3 square. Okay.
Okay, sir.
So this is called as prime factorization. So I get prime factors of a number, and therefore every number I can break into primes. So primes are important. If I understand properties of primes, I'll understand the properties of all integers. That's one fact, one thing. Then secondly,
Sir, what is the use of prime numbers in real life? Like,
yes,
Excuse me, sir.
in real life, for example, one can use them in security systems or crypto systems. That is the use. But let me tell you, till 1950, number theory or primes, etc., that was not used in real life. So it was supposed to be purest branch of mathematics, not at all applied. But nowadays, particularly after 1960, they have started using it in crypto systems. So, like for example, whenever you insert your ATM card in bank ATM, so you put some password, etc., and they are all converted into some different numbers just for security purpose. And all these things are done via some properties of primes. So maybe later on, if time permits, I'll try to explain how, or it's based on what idea. So this branch of mathematics and computers is called as cryptography.
Sir,
Yes.
sir, is it in where we hash a value?
What?
Sir, is this in where we hash a particular value?
What do you mean? I'm not following your question exactly.
Sir, is this the branch where we hash a value to convert it from one state to another?
Oh, acha, yeah. So for example, if you want to send some message, or for example, when you join some meeting via your email ID, and you put some password of your for your email ID. So all these things are converted. So for example, if if your password is something like this 1729, that will get converted as something else in the system on your computers, and that's the idea behind this cryptography. So your transactions, communications, etc., are safe. That is the idea of cryptography. For example, nowadays many people now do transactions through mobile phone. And
Sir,
yes.
one doubt, sir. For what and all we using prime numbers?
So yeah, I'll explain later, like exactly what's the idea or how they get used in cryptography. So maybe if time permits later on, I have some more problems where I'll try to explain how it's useful in cryptography. Okay, so far good. Shall we go one step further?
Yes, sir. Yes, sir.
Now there is one interesting idea called as sieve of Eratosthenes to find primes up to given number n. So given n.
So what is the question? I cannot hear your voice, sir.
given number n, how to find all primes up to n. And here is one nice idea which was used or which was introduced by Eratosthenes, who was from Egypt. He was the chief librarian. He was a very learned person, chief librarian of Library of Alexandria. Where is Alexandria? Egypt. Library of Alexandria, Egypt. And his period is little before Euclid. It's 276 BC to 194 BC.
That's the period when Egypt.
Yeah. So let's try to understand the idea of sieve of Eratosthenes. So given n, you have to keep cancelling multiples of prime numbers up to root n. So for example, in this case, our n is 100. We are finding primes up to 100, and therefore we have to cancel multiples of numbers up to root of 100, that is 10. Okay, so let's see what was his method. Method is simple, but very interesting, very ingenious. And of course, nowadays, there are many other tools, many other methods to find the primes, as well as nowadays people make use of various apps or calculators, computers, etc. for finding primes. Yeah, so let's see what was method. 1 is not prime by definition, and the first uncut number 2 is prime. I think some of you, if you are in
We
CBSE,
have to cross out all the multiples of 2.
yeah. So I think some of you, if you are in CBSE or ICSE schools, you must have this table in your regular school syllabus.
Yes, sir.
Okay.
Sir, we had it in 4th and also 5th and also in 6th.
Oh, very good. Very
Sir,
good.
I added in 5th.
So what is your this one board CBSE?
What's it?
What is your board CBSE?
Yeah, sir, it's CBSE.
Sir, in my ICSE, I also have the same.
Oh,
We had it in 5th grade.
okay.
Same
Okay.
fifth grade.
Yeah. So now idea is following. So once 2 is prime, all multiples of 2 they can't be surely primes, right?
The composite.
Yeah, they are composite.
So
So
we cross out.
So I'll cancel out all multiples of 2. They cannot be primes. So numbers ending with 2, numbers ending with 4, numbers ending with 6.
With 8 and 0.
Yeah, I should cancel all the numbers.
2, 4, 8, 6, and 0.
Yeah.
2, 4, 6, 8, and 0.
So we cancel out all such multiples of 2. And then the very first uncut number is prime again. And what is that number? That is 3.
3.
Right?
3 is prime.
Yeah, so 3 is prime. So you see 3 is not cut, and that is prime.
And the others all are cut.
Now again, same idea.
the multiples of 3 are cut.
6. 6 and
Yeah,
9
so
should be cut.
same idea you do
Nine is
with
cut.
3. Multiples of 3 now cannot be primes.
Yes, sir. 9 is cut. 9 is cut.
So 3 2s are 6, but 6 is already cancelled. 3 3s are 9. So
9 is
all odd multiples of 3 will cancel. Even numbers are already cancelled. So 9, 15, 21. I'm cancelling. You just check if I'm missing something. Then please tell me. 27.
All
30.
multiples of 5 also will be cancelled. Sir, 81.
Yeah, wait. So we are first cancelling the multiples of 3. 39, 42, 45, 48, 51, 57, 63, 69, 75, 78, 81, 87, 93, 99. Have I cancelled all multiples of 3?
Sir, we can cancel all the multiples of 5 also.
Wait. So have we cancelled all multiples of 3?
Yes, sir.
Yes.
Yes.
Yeah. So now the first uncut number, that is prime. And that is 5. Now once 5 is prime, all multiples of 5, they will be composite because 5 is proper factor. So cancel out all multiples of 5. And that is all numbers ending with 5 or ending with 0. But ending with 0 already we have cancelled. They are all even numbers.
15, 35, 45, 60.
Yes, I have cancelled all multiples of 5. And now,
7.
what is the first uncut number? That is 7. 7 is prime. Again, cancel out all multiples of 7. Just
14.
check. Yeah, so just check which multiples of 7 are yet uncut. 77, 91. Is everything cancelled? All multiples of 7?
Yes, sir.
Yeah. So now up to 10 there is no further prime, and therefore we have cancelled all multiples of primes up to
11.
root of 100, that is 10. Okay. So everything left is now prime. So let's check. 11. All
All are over, sir. All are cut.
yeah.
Yes.
So all uncut numbers, they are primes now. 13, 17, 19, 23,
23, 29,
29,
31,
31,
37,
37,
37,
41,
41,
43,
42,
47,
53,
53,
47,
53,
53, 59,
59,
59,
61,
61,
67,
67,
7,
21,
71,
73,
73,
23,
and
79,
29,
83,
83, 89,
89,
and 97. 89 and 97.
97.
So
Check
the
once again.
25.
Check once again through your list of prime numbers whether we have listed all primes between 1 to
We have
100.
listed all.
Yes, sir.
Yeah. So this is one interesting method called as sieve of Eratosthenes. It was method devised by Eratosthenes, who was chief librarian of Library of Alexandria, Egypt. He was not by profession a mathematician. In fact, he is more famous for his calculation of circumference of Earth. So he calculated the circumference of Earth.
Oh.
And there is even videos are there on YouTube, short videos, almost like 4 or 5 minutes videos. And his experiment was a very genius experiment. So he calculated circumference of Earth as, so his answer was 39375 kilometers. In fact, original answer was in stadia, the unit used in those times, 39375. It was some 800 or 8,000 stadia, I think 8,000 stadia, and which converts as 39375 kilometers. And you can imagine in those days, without any instruments like today's or telescopes or some computers or various modern instruments, that was a great feat. And with modern techniques, the same answer is modern calculation says the circumference is 39941 kilometers.
That is very close.
Yeah, so you see, it was so close. In fact, if you compute the error, it's less than 1% of actual. So he was more famous for this achievement.
So the circumference of Earth changes by 0.5 centimeter every year.
Wow.
Oh, I don't know much about, or I don't know much about other fields except this particularly maths.
Sir, this sieve of Eratosthenes.
That was finished.
This is a way to find primes.
Yes.
From that function pi. It's a good way to use that, but it will take time and it's not very efficient for large numbers.
Very good. Yeah. So that's a very nice point. In fact, for large values of n, this takes practically,
So days.
yeah, practically it takes a much long time. Or even if, for example, if you want to verify given number n, whether it's prime or not, even for that you need a lot of time. And in fact, various crypto systems, they are based on this idea. So let me tell you just work of 3 Indians. These are people from IIT Kanpur, and around 2002-2003, they developed one algorithm which gives whether given number n is prime or not in reasonably good time. Yes.
Excuse me, sir.
Yes.
Sir, can you please show the previous page? I need to
Wait.
see that table. sir.
Yeah, wait.
Even my father used to be an IIT Kharagpur. Sir, in 1993 something.
IIT Kharagpur, no, I think these 3 people are from IIT Kanpur. Agarwal, Kayal, Saxena. Agarwal, Kayal, and Saxena. So that is called as AK's algorithm. And the name of their paper is Prime Season P. So given number n, whether it's a prime or not, that is decided by some algorithm, which is polynomial time. Polynomial time means it's given in some reasonable time or practically smaller time. Yeah, I'm going back to earlier page. Some people wanted something from that page. Is that done?
Yes, sir.
You go ahead. Once the audio is on. Yes, shall we go ahead now?
Yes, sir.
Yes.
So some simple problems, and side by side I will keep explaining the theory or maths associated with those problems. Yeah, so which of the following are primes? And there are some typical type of numbers you see: 2 square minus 1, 2 cube minus 1, 2 raised to 4 minus 1, 2 raised to 5 minus 1, 2 raised to 6 minus 1, 2 raised to 7 minus 1, 2 raised to 8 minus 1, 2 raised to 9 minus 1, 2 raised to 10 minus 1, 2 raised to 11 minus 1. So numbers are of the type 2 raised to n minus 1. And such numbers were studied.
For Mersenne primes.
Yeah, so by a British mathematician. In fact, he was not mathematician by profession. He was some church person, but he was interested in mathematics, and he studied these kind of numbers for candidates of primes, and these numbers are known as Mersenne numbers. And whenever they are primes, they are called as Mersenne primes. So
Sir,
if
how to solve this?
it is prime, wait, I'll explain everything. If such number is prime, that is called as Mersenne prime. Okay. Now, a simple but nice result about these numbers is if n is composite, and I want to verify this fact through all these examples. If n is composite, then 2 raised to n minus 1 is also composite. But if n is prime, sometimes 2 raised to n minus 1 is prime, and sometimes it is composite. So we'll see such examples in this list. So sometimes 2 raised to n minus 1 is prime, sometimes it is composite. Yeah.
Sir, but no, sir. 2 is prime, not composite. Sir, I thought 2 was composite.
Yeah. So shall I go ahead? Okay, so I'm listing all these numbers here. 2 square, which is 4. So 2 square minus 1 is 4 minus 1, that is 3. And is that a prime? 3 is prime, right?
Yes,
So you see in this case 2 is prime and 2 raised to 2 minus 1 is also prime. So that is this case, right?
Sir, I just had an observation. If like if the number which is subscripted over here, it's a prime number, then the answer is a prime number.
But interesting fact is not always. And Mersenne listed some such numbers. So in fact, Mersenne also himself made some 5 mistakes while listing all such numbers. But we'll see that every time if n is prime, 2 raised to n minus 1 is not prime. Sometimes it is composite. And those numbers are in fact little more interest because most of them get factored as product of 2 primes, and such numbers are used in RSA cryptosystem.
Excuse me, sir.
Yes.
Sir, so in all these, in this pattern, all these answers are prime only.
Let's see. So let me first just compute all these powers of 2, and then we'll subtract 1 and we'll check the nature of that number. So what is 2 cube? Yes.
Sir, I got the answers, but I got many big numbers and I can't figure out if they are prime or not.
No, these numbers are not so big. Let's compute. So 2 cube is 8.
8.
2 raised to 4 is double of that.
That's
That is
16.
And in fact, this is example of sequence of geometric progression. In next 2 sessions, we are going to see APGP, and essentially this is example of geometric progression. 2 raised to 5 is 32. 2 raised to 6 is 64.
Sir, I did the wrong way.
2 raised to 7 is 128. Just check whether I'm doing correct calculation. 2 raised to 8 is 256, double of that. 2 raised to 9 is double of that, 512. 2 raised to 10 is 1024. 2 raised to 11 is 2048. Minus 1, 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 minus 1. So 8 minus 1 is 7, and that is again prime. 16 minus 1 is 15, and that is composite. This is not prime. Okay, this is composite. It's not prime. And that is obvious because 4 is composite, and if n is composite, 2 raised to n minus 1 is composite. Is the result clear? If n number is composite, power is composite, 2 raised to n minus 1 is composite. So here we see 4 is composite, so 2 raised to 4 minus 1 is composite, that is 50. Then 5 is prime, 2 raised to 5 minus 1 is 31, and in this case we see it's prime.
Yes, sir.
6 is composite, so 2 raised to 6 minus 1 must be composite. Let's see, 64 minus 1, where is my cursor? Oh, yeah. 2 raised to 6 minus 1, 64 minus 1, 63, and 63 is 7 nines. So
Yes,
that is
sir.
not prime, that is composite. Those which are tick marks, they are primes. Those which are crosses are composites. Yeah, 2 raised to 7 minus 1, 128 minus 1, that is 127. Is that prime? 127?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Yeah.
Yes, sir.
So 127 is composite. And which means this is what case? 7 is prime, 2 raised to 7 minus 1 is also prime. So that is this case. Okay? 2 raised to 8 minus 1. Obviously 8 is composite. So this number must be composite. 256 minus 1, 255. And surely 255 is composite. Why? It ends with 5, so it's divisible by 5. Also, you can check sum of digits is 12.
It's divisible by 3.
Yeah, so it's
Yeah.
divisible by 3. Okay, so it's composite.
Yeah.
Then again, 9 is composite, so 2 raised to 9 minus 1 must be composite. So check 512 minus 1, 511. That is composite.
It is prime.
It's divisible by 511 is composite. It's divisible by 7. 7 7s are 49, 7 into 73. So it's composite. It's not prime. Those which are crosses are composite. Those which are tick mark.
Sir,
Yeah.
you have wrote here 511,
Yes.
but the answer you wrote means it's 572. So it should be 571, no?
No.
Why 571? No, it's 512.
That's 512. That's not 572.
512 minus 1. So that is 511. 511 is
Because it's looking like 7. You wrote here one, no? That.
no, it's 512. It's 512 minus 1. So 511.
Okay, I was confused because that.
Actually, yeah.
Okay, now 10 is again composite. So 2 raised to 10 minus 1 must be composite. And let's check. This is 1023. So obviously sum of digits is multiple of 3. So it's divisible by 3. I'm not factorizing it. It's surely divisible by 3. So it's not prime. It's composite. Yeah. And a very interesting example is 2 raised to 11 minus 1. Now 11 is prime. Check without calculators, without computers, check this number manually. 2047. Just a minute. Let me see something. Let me complete this. Yeah. So 2 raised to 11 minus 1 is 2047. And without any calculator or any app or any use of computers, manually check whether 2047 is prime or composite.
Sir, it's prime.
So that's composite.
Okay, so I'm giving you answer. This is not prime. This is composite. So this is first case where n is prime, but 2 raised to n minus 1 is composite. So this is the smallest example. 11 is prime, but 2 raised to 11 minus 1 is composite. And for certain reason, I want you to compute the factors without any help, without any aid, like calculators, any app, or on your or using Google or ChatGPT or anything. Okay, so calculate that without any help manually on your own, and that is the basic of cryptography. So those who get that factors, you can write in chat box only to me. Don't disclose the answer.
Sir, I sent you in chat box, sir. If my answer is correct.
With that, it's
Sir, I said.
it's not prime. It's not prime.
Oh, okay, sir. I
So,
think I made a mistake.
So let me give you answer. It's composite and it is product of two primes. So you have to find those two factors, prime factors, but manually, without any help, without any aid. Don't use Google, don't use ChatGPT, don't use calculator, and try to find the answer. So why I'm saying that? Because that is the basis of the RSA crypto system. So essentially, the idea of cryptography is where primes are used. The idea is to factorize a number into product of primes takes more time than the multiplication. So if I give you two numbers to multiply, you can do it in seconds or in minutes. But if I give you some huge number to factorize as product of primes, that takes practically a very long time. And in cryptography, they use huge prime numbers like which are having 400, 500 digit prime numbers.
Sir, I have said my answer.
I have doubt, sir, in homework.
Huh?
I have doubt in my homework, sir.
So I told you about homework. What you can do is, or what we expect is, as far as Olympiad is concerned, you try as best, as hard as possible.
No, sir, today's homework I have doubt, sir.
Which homework?
Sir, in third question and fourth question, sir.
No, which homework? Yesterday's homework?
Sir? Sir?
Yes.
I can't understand what you are saying, sir.
No, I'm asking which homework, yesterday's homework or which one?
Sir,
So-
yesterday, sir.
Okay, so once again, I'm telling all of you, you keep trying all those problems, and what we expect is don't look at ready-made answers, but surely after some days I'll give answers to all those questions as a PDF in your WhatsApp group. So, but as far as Olympiad is concerned, what's most important is you keep trying. For example, when in fact that time I was a teacher, when as a teacher I tried some Olympiad problem for the first time, it took almost 1 day or a half day. So don't give up. Have some perseverance and keep trying, because that will develop your thinking. Okay. Anyways, later on we'll give solutions or answers. Fine. So, but just getting ready-made answers is of no use for Olympiads. Anumega, these factors are not correct.
Yes, sir.
And in fact, 1001 is not prime. 1001 is 7 into 11 into 30. In fact, why I'm giving you this problem to check manually, the reason is basically you should understand that problems of cryptography or security systems. So essentially, if I want to factorize a number, that is difficult. But whereas if I'm given two numbers to multiply, that is easy. And the crypto systems are based on this idea. Okay, how do you check whether given number is prime or not, or how you factorize? Like for example, 2047. So you should try. You should try.
Sir, I sent an answer. Is it correct?
Just a minute.
Shrestha.
Sir, I'm Ahansh Agarwal. Even
Shrestha, yes, that is correct. Factors are not correct. You can multiply 3167 and check whether the answer is 2047. Because taking multiplication is easy, or it's a little less time taking. Yes, Shrestha, that is correct. Okay, so let me tell you how do you check whether 2 divides 2047? Surely 2 does not divide because number is odd. Then you check whether 3 divides it, and we know test of divisibility by 3. 5 surely does not divide it. Check 7, check 11, check 13, and so on. So even if you check up to 13 and you don't get any of them as a factor, have some patience and go ahead with 17, 19, etc.
Sir, I sent once again. Is it correct?
Wait a minute. No, wait. Surely 3 is not a factor. Why you are writing 3? Because sum is not divisible by 3. So let me give ready-made answer. Because I want to say something more about this Mercy numbers. So this answer is 23 into something. Now, smallest factor is 23. So once I am giving you 23 as one factor, you can find the other factor. So it's 23 into what? So one factor is 23. Check the second factor. It's 23 into 89.
I got that answer.
Okay. Yes. So let me say something more. On internet, there is a project called as GIMPS.
The photo editing something.
Short form for Great Internet Machine Prime Search. Great Internet Machine Prime Search. And it's a group of people who are interested in number theory as well as interested in coding, and they come together, they join their computers in parallel and work together on some such big numbers. So the last success was December 2016, where they found one Mersenne prime. It's a huge prime. So the latest known Mersenne prime is following. Latest and greatest. Mersenne prime is 2 raised to 8259933. 8259933. That's a prime number. -1. So we know Mersenne prime is of the form 2 raised to prime number -1. So this is prime. So that's the greatest known Mersenne prime, and it was found in December 2016 through this project called as GIMPS, Greatest Internet Mersenne Prime Search, Great Internet Mersenne Prime Search. It's a group of people, and they join together to work on search of Mersenne primes.
Sir,
Yes.
sir, can I raise Sir, can I raise 2 to this latest known Mersenne prime and then subtract 1 from it?
But practically speaking, finding 2 raised to 8259933 is a very tough job. In fact, it will be huge number. Let me tell you the number of digits. So number of digits is, so which has 2486 2048 digits. So even to write so many digits, even on laptops, that is a very difficult job. And further to check whether it's prime is again another tough job. So because they join in parallel and work together, these things are possible.
Sir, in which day and date they found, sir?
I guess I think 16 December. This fact you can check on internet. You can check on Google later. Or if something has been found after 2016, I don't know the recent one. Yeah, so that's about one type of primes, namely Mersenne primes. We have 10 minutes more. We'll try to solve 1 or 2 simple questions. Yeah. Alice was 2 years younger than Bob. If they lived for 100 years, how many times ages of both were prime numbers? So such primes, so just note, if Alice has age which is prime number, say P, even Bob has age which is again prime number. And Bob is 2 years elder to Alice. So Bob will be P plus 2, right? and such pairs P plus 2 both primes. If P plus 2 are both primes,
So their ages must be twin prime numbers.
they are called as very good. Yeah. Who was that?
Deshna.
Deshna, yes. So they are called as twin primes. And let me tell you unsolved result related to twin primes. In fact, one knows there are how many primes? There are infinitely many primes, and there is a conjecture which is yet unsolved. What is conjecture? A result which is still not proved, neither disproved. Conjecture. There are infinitely many twin primes.
So it seems like that this conjecture is true.
Yeah, in fact, one Chinese person claimed, I think in 2013-14, that yes, he has solved it, but so far, experts have not given a nod for that.
So if they're infinite prime numbers, then they should be infinite twin prime numbers.
Why is that so? So, I mean,
Because as long as there are prime numbers, there are also going to be twin primes that occur with the
but
prime.
why later on after some stage there will be some more gaps in primes and not just difference of two?
Yes, sir. But even if there are more gaps, there will still be infinite primes because at one point or the other they will occur.
See, primes will be infinitely many, but that does not mean you'll always find numbers of the form P plus 2 continuously infinite. Okay. So, of course, they are checked using calculators, using computers up to certain lakhs, and they haven't found any counter example. So it's a conjecture. It's not disproved yet, and neither it is proved yet.
That's fine.
Yeah, so we want cases up to 100. They lived for 100 years. We want cases up to 100, and all those primes are already available with you. I hope all of you are written in your notebooks. So Alice and Alice plus 2, both numbers should be primes. And very first such pair is 3, 5. Then when Alice would be 5, Bob would be 7. So again, both are primes.
11, 13.
11, 13.
Sir, don't you just have to multiply 25 into 2 and
17 and 19.
17, 19.
19.
Just a minute. Someone said about multiplication of something.
Sir, can't you just multiply 25 into 2 and then you'll get the answer?
For what?
31, 33. 31, 33.
33 is divisible by 3 and 11.
Oh, yeah.
41 and 43.
29 and 31.
What is next to 17, 19?
Sir,
29,
39.
29, 31, right?
Then
41 and 43.
41, 43.
43, 41.
47, 49.
49 is 7 square.
9 is not prime. 49 is not prime.
Sir, 71 and 73.
59, 61.
61.
Sir, then also 70.
71 and 73.
71, 73. Yeah.
Sir, that's it.
71 and 73.
So how many times up to 100 we get twin prime pairs? 8 times, right? So how many times ages of both were prime numbers? 8 times. Right? There is no other pair.
Yeah, probably.
Sorry.
And we have what that is.
So we'll do
Sir,
979 will not come.
81 is 9 square.
81 is not prime. You have list of prime numbers with you.
So that's it.
Yeah,
that's it.
we get 8 pairs between 1 to 100.
5, 3, 5, 7, 11, 13, 17, 19, 20, 31. Yeah. 12, 71, 30.
Okay, so we'll solve one more simple question, but again that tells about some result. Write 100 as a sum of two primes. And problem is simple, but let me tell you the theory behind it. That is again some conjecture. It's due to a German mathematician Goldbach. So they pronounce it as Goldbach.
Then 47 plus 53.
Wait. Just listen to the theory part first, and then we'll solve the question. Question is simple that everyone can. So there is a statement called as Goldbach conjecture. Somebody's audio is on. Please mute your audio. Yeah, thank you. So there is a nice statement called as Goldbach conjecture. And what is conjecture? It is still neither proved nor disproved statement. Okay, so which says statement is simple. Every even number greater than 4 can be expressed as sum of two primes. As a sum of two primes. So for example, 4 I can write as 2 into 2 plus 2. 6 I can write as 3 plus 3. 8 I can write as 3 plus 5. 10 I can write as say 3 plus 7 or 5 plus 5. So which means at least first 4 even numbers up to 10, we have checked that each of them can be written as expressed as sum of two primes. Okay, sometimes in more than one ways. And we want to do the same thing with 100. So I want to write 100 as sum of two primes. Yeah, so now you can go on telling.
Sir, I said my answer. Darshan, is it correct?
You can tell orally all answers, all possible answers.
So the answer is 47 plus 53.
Yes, sir.
47. And there is no unique answer. You tell all possible answers. 47.
97 plus 3.
Yeah, very good.
89 plus 11.
3 and 9 plus
59 plus 41.
Wait. One by one. 97 plus 3, that is correct. Yeah.
89 plus 11.
89 plus 11, correct.
39 plus 41.
39
plus 41.
17. 83 plus 17.
59 plus 41, is that correct?
83 plus 17. 83 plus 17.
83 plus 17, yeah, that is correct.
29 plus 71.
29 plus 71, that is correct. What else?
$37 and $59, sir.
No. 37 plus 59 won't be 100.
Sir, 71 and 29.
No, that we have written. That is last page. 29, 71. Anything else?
No.
Yeah, so
I think that's all the possible answers.
yeah, so these are the 6 possible answers, right? So there are 6 possible ways for 100. Okay, and anyways, the results, Goldbach conjecture says
Sir,
we can express it as sum of two primes. No, in how many ways that is not given? Yes. Yes, somebody was saying something.
sir, I am Anamika. I have
Anamika.
one answer, it's 31 and 69. That's correct.
69 is the not prime. It is divisible by 3.
69 is not a prime.
Yeah.
3 into 23 is 69.
Yes. Okay, so it's already time now. So we'll stop here then. I hope you enjoyed properties of primes, and so I have given you 2 results which are still conjectures. So perhaps some of you later on, if you go into research in mathematics and if you are interested in number theory, you can try to solve these 2 conjectures.
Yes, sir.
Yeah. So shall we stop for today?
Yes, sir.
Bye.
Sir,
Thank you, sir. Bye, sir. Thank you, sir. Bye, sir.